Okay, let's unpack this. For years, the reigning orthodoxy in modern information retrieval has been, well, it's been a pretty simple mantra, right?
Oh, absolutely. Especially in the world of neural search.
It was always dense vectors generalize better.
So just give us more dimensions, more data.
Bigger pre-trained models.
Yeah.
The assumption, I think, was always that any failure, in these complex retrieval tasks was just an engineering hurdle.
Exactly. We've seen this whole shift from sparse methods like BM25 towards these dense neural language models. But then you throw a really complex task at them, like, say, the reasoning in Bright or instruction processing in Quest.
And they struggle.
They struggle, and the consensus was always, oh, we just need better contrastive loss, or we need better negative sampling.
And now this crucial paper from Google DeepMind on the theoretical limitations of embedding-based retrieval has just, well, it's fundamentally challenged that entire consensus. So the core mission of this deep dive is to really rigorously dissect their mathematical argument, which is that the inability of these single-vector embeddings to handle certain tasks isn't about training or data.
No.
It is a hard, unavoidable theoretical limit, and it's tied directly to the embedding dimension.
This is truly foundational stuff, because the whole shift to dense retrieval rests on this single vector capacity idea.
Right.
We take a query, we take a document, we squeeze them each into a single vector, and then relevance is just the dot product, a geometric proximity metric.
But the paper argues that this very reliance on geometric space has predictable mathematical limits, especially when you move beyond simple keyword matching and into, complex arbitrary instruction following.
Yeah.
So we have to start by formalizing that constraint. How does classical learning theory, specifically matrix, rank put a measurable limit on these modern vector spaces? The whole argument seems to hinge on the rank of the relevance matrix.
It does, and we need to be precise here. So let's define the problem mathematically. Imagine you have null queries and other documents.
Okay.
The ground truth, what's relevant and what's not, is all captured in this binary matrix, your basic curl matrix.
And a dense retriever is trying to reproduce the ordering from that matrix using its own score matrix, B, which is just the product of the query and document embeddings.
Right. $by equals UTV. And since your query matrix own null is times nuller, and your document matrix ours is nuller and nuller not.
The dimension of the embedding space has to be at least the algebraic rank of that score matrix, all or dollars. The capacity is constrained right there by the algebra.
That is the key structural constraint. So the paper introduces two formal measures to quantify just how difficult a matrix dollar is.
Okay.
First is what they call rank RUP, the row-wise order-preserving rank. It's the minimum rank that you need for your score matrix to perfectly preserve the order in every single row of A.
So for any given query, all the relevant docs have to score higher than all the irrelevant ones.
Exactly. And the second one is the row-wise thresholdable rank.
Which sounds similar.
It is. It's the minimum rank dollars you need so that for every query, you can find some threshold tau that cleanly separates the scores of relevant and irrelevant documents.
So one is about relative order, the other is about a clean cutoff.
And the first really elegant result in the paper, Proposition 1, is that for binary matrices, they're the same. Rank A equals rank A.
That's clean. It confirms that whether you're thinking about preserving order or just separating classes, the minimum dimension you need is the same.
Right. But actually, calculating this rank is hard. So to establish bounds, we have to turn to the sign rank.
The sign rank, and that's a concept from complexity theory, right?
Exactly. We take our binary relevance matrix, $8, and we transform it into what's called a bipolar matrix, $, which is just full of plus ones and minus ones.
So why $2 8 EA?
Yep. The intuition here is that sign rank is measuring the algebraic complexity you need just to recover the sign of the relevance. Is it relevant or not using a lower rank representation? It tells you how complex the geometry has to be to keep positive and negative classes separated for every query all at once.
And Proposition 2 in the paper gives us the critical link back to the embedding dimension, $.
It does. It establishes the central chain of inequalities. The key thing for you to know is that it provides concrete lower and upper bounds on that order-preserving rank we talked about.
So if you can compute the sign rank of your relevance matrix,
you've mathematically defined the minimum dimensionality dollar you're going to need to perfectly capture those retrieval relationships.
So if we just step back for a moment, the big takeaway from this theoretical section is that some retrieval tasks, just because of their combinatorial complexity, will produce a Krell matrix with a really high sign rank.
And that makes them intrinsically more difficult.
Right. It's not about the language in the query being hard. It's about the sheer pattern of relevance you're asking the model to represent. The geometry is constrained, and the sign rank gives us the hard proof that for any fixed dimension dollars, there's some relevance matrix dollars that you simply cannot capture.
That is the mathematical floor, an unshakable lower bound.
So, if the algebra sets the floor, the logical next question is, what's the ceiling? What happens if you remove all the linguistic constraints and just directly optimize the vectors? What could DABL possibly achieve in a perfect best-case scenario?
And this is where they came up with the free embedding experiment, which is, it's just a crucial piece of this puzzle.
Because it abstracts away all the messy parts of pre-training.
Completely. They just treated the query and document embeddings as totally free parameters. Then they used gradient descent atom, influence E-loss, to optimize them directly on a synthetic Krill matrix. They were asking, what is the absolute largest number of documents NAS we can handle in a dimensional space, even if the vectors don't have to mean anything in terms of natural language?
So it's an idealized upper band, a ceiling that no real-world model which has to generalize from language could ever hope to actually reach.
Precisely. And the key metric they used was something they called critical N.
Which is?
It's the maximum number of documents, non-null dollars for a given dimension, non-null dollars, where the optimization can still solve all possible top-tack combinations. And because of the combinatorial explosion, they focused specifically on the case where K...
But when they ran this across different dimensions, they found a relationship between new dollars and this critical N.
Yeah.
And the fit was astonishingly precise.
It was an excellent fit to a third-degree polynomial curve. The 2 was 0.9999. But the resulting equation, it tells a pretty devastating story about scalability.
Because the capacity only grows cubically with the dimension.
Yes, polynomially.
But the scale of modern web scale data, it grows exponentially. A cubic relationship is just, it's not enough. This mathematical fit confirms you run into diminishing returns so fast.
The numbers really drive it home. They extrapolated this ideal model out, and the limits for standard dimensions are, well, they're tight. For a common dimension like 200-244 was, the extrapolated critical N is only around 4 million documents.
4 million. That's the absolute theoretical maximum number of documents where you could perfectly separate all top two pairs. And for a very large dimension, say 2D 40996
the ceiling only goes up to about 250 million documents.
Wow. That's the mic drop moment for web scale retrieval. If your system has to be able to model all possible combinations in a massive corpus, then our current embedding sizes, even if they were perfectly optimized without language, are fundamentally insufficient.
It proves the bottleneck isn't just how well you encode the language. The bottleneck is the dot product similarity function itself when you're trying to model complex combinatorial relevance.
Okay, so we have a theoretical floor from SignRank and an ideal ceiling from this free embedding experiment. Now let's ground this in reality. What happens when you hit actual state-of-the-art models with a real-world version of this problem? This brings us to the limit dataset.
The limit dataset was the empirical hammer they built to test this theoretical nail. The whole goal was to create a dataset that, even though it used simple natural language, had a Krell pattern that was maximally dense. It embodies that high sign rank complexity the theory predicts should be impossible for single vector models.
So they didn't rely on the complexity of the text, but the complexity of the structure. Tell us about how they designed it for that Capriel Dunk case.
The design was ingenious. They have 50,000 documents and 1,000 queries. And to max out the combinations for KL22, they focused on a small set of just 46 core documents.
46. Why that specific number?
Because 46 choose 2 is 2035.
Huh.
So with 1,000 queries, they could explicitly construct queries to cover almost every single unique pair combination of those 46 documents. This forces the retriever to learn a high sign rank pattern. It's structurally dense and maximally demanding on the geometric space.
How did the big models do? The champions of dense retrieval, like Gemini Embed, Grid-LM, E5 Mistral.
The results were strikingly poor. On the full data set, where you have to find one of those 46 docs from the 50,000, these SOTA models were just struggling, barely hitting 20% recall at 100.
And even on the small version, with just the 46 documents.
Even then, they fell far short of 100% accuracy. They just couldn't solve the task completely.
Now, whenever a model fails on a synthetic data set, the first criticism is always, it's a domain shift problem, the model just failed to generalize. Did they rule that out?
They absolutely did, and in two very clever ways. First, they actually fine-tuned a model on a limit-style training set. If it was just domain shift, that should have helped a lot.
It didn't.
It barely moved the needle. The model only reached about 2.8, recall at 10. This is strong evidence that even if the model knows the linguistic style, it just can't encode the required pattern.
And the second piece of evidence was even more compelling, right?
Right.
Contrasting the dense pattern against simpler ones.
That's the definitive proof. They tested the models on the dense pattern versus 3 other simpler patterns: random, cycle, and disjoint. On the simple patterns, the models did fine. But the second you switch to the dense pattern, performance collapses.
How bad was it?
For GridLM, it was a 50 absolute percentage point drop in recall at 100 compared to the non-dense patterns. It's devastating.
So that confirms the central thesis. The architectural limitation only rears its head when the model has to capture a relevance matrix with this complex algebraic structure. It's a math problem hiding inside a language task.
Precisely.
So, theoretical proof, empirical failure. What does this mean for the future of retrieval? If the single vector paradigm is fundamentally flawed for these complex tasks, what's the escape hatch? What architectures can get around this dollar constraint?
Well, the paper's concluding section looks at exactly that: architectures that don't rely on a single dot product.
Let's start with the one that actually solved the task, the cross-encoder.
Right. Cross-encoders, which are usually used as re-rankers, they completely overcome the dollar limitation. That's because they're reevaluating the query and document together, contextually. It's a full forward pass on the pair.
It eliminates that constrained geometric projection.
Exactly. And the authors showed that Gemini 2.5 Pro, when used as a cross-encoder on that small set of 46 documents, got 100% accuracy in a single forward pass.
That's the smoking gun. It proves the task is linguistically simple, but geometrically impossible for single-vector embeddings. The trade-off is, of course, they're incredibly expensive.
Way too expensive for first-stage retrieval on a massive corpus. So the constraint isn't the model's linguistic ability, it's the efficiency we demand from first-stage retrieval.
Okay, so what about models trying to bridge that gap, the multi-vector models?
They showed promise. Something like GTE Modern Colbert scored significantly better than the single-vector models on Limit.
Suggesting that having multiple token-level vectors helps a bit.
Yeah, it seems to distribute the representational load, easing that single-vector bottleneck. But they still struggled to solve the task completely, so it mitigates the issue, but doesn't seem to fully solve it.
And then there's the old guard, sparse models.
Sparse models like BM25 did near perfectly on the Limit dataset.
Why is that?
Because you can think of sparse lexical vectors as having an inherently very, very high dimensionality. All those zeros give them a ton of capacity, so they just sidestep the low-dimensional constraint that handcuffs the dense models.
The big question there, though, is still how you apply them to instruction-following tasks where there's no lexical overlap.
That's still an open research question, but this all leads to the core implication for you, the practitioner. We're seeing this rise of instruction-based retrieval reasoning tasks, and these are forcing models to represent a whole spectrum of complex logical relevance. That means encoding Krill matrices with arbitrarily high sign rank.
So the results really necessitate a foundational move away from the single-vector paradigm, at least for any task that needs to capture a high number of these complex top-K combinations.
The paper has given us the mathematical proof. The geometric constraints of a single dot product just cannot handle the combinatorial explosion of relevance definitions we need for modern IR.
Okay, so to summarize this deep dive, we started with the theory, the minimum dimension required, which comes from the sign rank of the relevance matrix. Then we showed with the free embedding experiment that even a perfect idealized model fails at web scale because of that cubic capacity growth.
Right.
And finally, we saw empirically that state-of-the-art dense models fail spectacularly on the structurally dense limit dataset, proving this isn't just an empirical problem, it's a foundational mathematical hurdle.
It's the proof the community really needed. And while the authors acknowledge their theory doesn't yet cover everything, like multi-vector models or error tolerance, we now have mathematical certainty. Some combinations of top-kill documents cannot be represented by our current single-vector models, and knowing that, it forces a radical shift in perspective.
It does. The fundamental challenge is no longer just how do we make bigger embeddings, or how do we tune our loss function better.
The new retrieval frontier is now clearly defined by this tension between efficiency and capacity. How do we design an architecture that keeps the speed of dense retrieval but has the representational capacity for these high sign rank matrices? And so the provocative question for you, the expert listener, is this: what new hybrid methods can solve this problem? Can we combine structured sparsity or multi-vector interactions or maybe new non-dot product scoring to solve this high sign rank problem efficiently without having to pay the massive computational cost of cross-encoders at the first stage? The architecture now has to catch up to the mathematics.